Good morning, children. So today we are going to discuss about trick of VBT in complexes. So we have already discussed before about valence bond theory. If you try to recollect, valence bond theory helps us to figure out the hybridization in complexes. So I'm writing down here for you hybridization. When we come to know about the hybridization of complex, we can also find out its shape. And another very important factor is its magnetic behavior, whether the complex is paramagnetic or diamagnetic. Apart from that, valence bond theory also help us to know whether the complex is outer orbital complex or inner orbital complex. So these are the few objectives of VBT for coordination complexes. But what is the main deciding factor which is so much influential that it is going to decide the hybridization, the magnetic behavior, or even the nature of the complex? So this is if I'm talking about the nature of the complex. It's only the ligands. And I already taught you before that ligands have been widely classified as strong field ligand. Okay, I'll write down here strong field ligand and weak field ligand. If the ligands are strong field, then there is a concept of pairing. That means the electrons in the d orbital of central metal ion gets paired up. And for the weak field ligands, no pairing is observed. That's very important point to decide the hybridization in coordination complexes. Another important thing you should also remember at the same time, if the ligands are strong, okay, if the ligands are strong, they are said to be low spin. Remember this. And weak ligands are said to be high spin. What exactly is meant by low spin and high spin, we will be learning in this video. So keep watching. Let me set the next page for you so that I can work out few examples for you. So here we go. So the first example which I would like to give you is about this complex CONH3 whole 6 with +3 charge. Okay, now the central metal atom, it's very clear, it's cobalt, and the ligand is amine. Now remember the tricks to be followed. So trick number 1 is find out, okay, I'm writing down here, find out the oxidation state, the oxidation state of metal ion, oxidation state of metal ion. Okay, once you are set with it, then see the ligand what you have. Okay, that means look at the nature of ligand. Now here in this example, the ligand is amine, and I gave you the series of weak field ligands and strong field ligands. So please get back to that series. If you have not learned, you need to learn that series. Now we understand that amine is a strong field ligand. So amine is a strong field ligand. If it's a strong field ligand, what is going to occur? Pairing of electrons. These are the two very important tricks to be followed. Now let us go with the configuration. So the central metal atom is cobalt here, right? and the atomic number of cobalt is 27. So if I want to write the configuration, I will write it as 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d7. That's the configuration of cobalt. Now, we don't have to bother about the inert configuration till here. So if you see, instead of writing all this, what can you write? 6 plus 2, 8, 8 and 6 plus 2, 8 again, 16 and 18. The total number of electrons in this box are 18, and that's the configuration of argon, right? So instead of writing this whole, I can also write it as, I will just erase this and make my things very clear and easy so that I don't have to bother about this part. I will just write here argon and 3d7 4s2. And this you already know that 4s is filled first before, okay, we consider 3d. It is because of the rules, that is n plus l rule, and of course the Hund rules will be applied here now, which you have already learnt in grade 11. So now let us see the oxidation state. So the first step is to calculate the oxidation state of the central metal atom. So it's cobalt is X, amine is 0 into 6 equal to plus 3. So the value of X is plus 3 here. So cobalt is in plus 3 state. That's a cobalt ion. So what will be the configuration now of this cobalt? Let me write it down here. It will be argon, right? And since 4s orbital is filled first, but yet it remains the outer shell. 4 is the outer shell. So first of all, electrons are removed from 4s, and then only we can think about 3d. So when we remove the electrons from 4s, 2 electrons are lost and the configuration becomes 4s0, wherein one more electron is removed from d, which becomes 3d6. Okay, now if you remember, when I was teaching you VBT, I taught you there are set of 2 orbitals which are participating. The 2 set of orbitals. One was n minus 1 d ns np. So here is that series with us. Okay, so I'm going to write here also 4p0 because there are no electrons present, but I have to consider it because I need how many ligands over here? I have 6 ligands, right? So that's the reason I have to mention it like this. So I'm going to erase it. This is just for your reference. Okay, now what should be the next step? The next step should be the filling in of electrons. So when I try to fill in the electrons, I'm going to draw the orbitals, and we know in D there are 5 degenerate orbitals. Okay, so here is my 3d. This is here. I'm going to erase it. Let me make it a little bit symmetrical. Okay, now here it's your 4s, and the next one is your p, 4p. Okay, good. Now how many electrons are there in D? There are 6 electrons. But what is the nature of the ligand I have decided here? It's a strong field ligand. And strong field ligand means what? Pairing should happen. So by Hund's rule, the orbitals should be first singly filled and then only pairing should happen. That is what we have learned before in grade 11. But now, in case of coordination complexes, these ligands are so much influential that we don't have to bother about the Hund's rule. We have to go as per their nature. So I said strong field ligand means pairing of electrons. So understand it very carefully how pairing actually occurs here. So I'm going to use a different pen for you. Now see here, two electrons in each orbital should be filled, then only it should move to the next orbital. So 1, 2, 3, 4, 5 and 6. So this is how the arrangement of these 3d6 electrons is shown in this figure, right? Now the concept of hybridization, as I told you, according to VBT, means mixing of the orbitals. So how many orbitals should mix? That is again decided by the coordination number. So since the coordination number over here is 6, so that means 6 orbitals should hybridize. So where should I find 6 orbitals to be hybridized? And remember one more thing, the orbitals which will hybridize should be totally vacant, empty. It is because ligands have lone pair of electrons. So since they have lone pairs, so each ligand will donate 2 electrons and the maximum capacity of each orbital is only 2, right? So that's the reason how many orbitals I need. I need only 6 orbitals to hybridize together because I have 6 ligands with me. So which are those 6 orbitals? I'm going to mark here. These are the 6 orbitals which are going to hybridize together. So when they hybridize together, what are you going to get? You are going to get 6 hybrid orbitals. So 1, 2, 3, 4, 5 and 6. Okay, so here 6 hybrid orbitals. And what is the hybridization? I can write down here D2, because 2 orbitals of D and 1 orbital of S and 3 orbitals of P got hybridized, and therefore the hybridization is D2sp3. And here, which are the ligands? Let me use this color for you. The ligands are NH3. How many ligands I have? 6 ligands. So each of these ligands over here will donate 2 electrons to each orbital. Okay, so here I have NH3 with me. Okay, so each of these orbitals will gain 2 electrons from these ligands and the octet becomes complete. Therefore the bonding is done. So the metal atom is very, very important. And we also understood that how important is the oxidation state over here. So oxidation state and the nature of the ligand are the basic factors which is deciding the concept of hybridization. Okay, now in this case, since the hybridization is D2sp3, so I will use this space. Okay, I'm going to erase all this for you because this is already done. Okay, now which is the hybridization I landed up? I landed up with D2sp3, and in the previous video I already discussed if the d orbital is the inner orbital over here. Okay, as we got here D2sp3 hybridization, and the d orbital is the inner one, that's 3d, so it is inner orbital complex. That's very, very important point. So I conclude that it's a inner orbital complex based on the hybridization. Next, I said the magnetic behavior is also one of the objectives of VBT. So here you have to check the 3D, okay, 3D orbital of the central metal ion. So in 3D orbital, all the what electrons are paired up. There is no unpaired electron. So its nature is dimagnetic, because I repeat again, because all the electrons in 3D orbital of the central metal atom are paired, therefore its nature is dimagnetic. So we come to know that it's an inner orbital complex. Its magnetic behavior is dimagnetic because all the electrons in 3D orbital are paired, and of course the hybridization is D2sp3. So what should be the shape? The table which I discussed previously helps us to understand that the shape is octahedral. Okay, so octahedral is the shape of this coordination complex. So this is how we come to know about the parameters of this complex. I hope it is very clear to you. But this is little difficult topic, so I would like to give you one more example. So please keep watching. Let me set a page for you. Okay, here we go. Let us take another example of, maybe I can give you a few more examples as well. Now I would like to give you the example of let us say CO, that's again cobalt, F6, okay, that is florido as your anion, and the charge on the complex is say -3. Okay, let us take this example. So again we move on to the same thing what I discussed in the previous slide. So first of all, write the configuration of cobalt as its argon, and here we have 3d7 and 4s2, right? Initially it is 2. Now let us calculate the oxidation state. So oxidation state is X, and fluorine has -1 charge, florido as a ligand to be named, into 6, because 6 ions are there, equal to -3. So X comes as again +3. Okay, so again cobalt is in +3 state. So what should be the configuration? So I'm going to use the same space here to write the configuration. Okay, I've erased all this. So here I write +3. So 4s will become 0 and 3d will again have 6. Now next thing is the nature of the ligand. So ligand here is florido, which is a weak field ligand. Okay, according to that series which I mentioned before, you have to learn. So it's a weak field ligand. So what did I tell you before? If it's a weak field ligand, then there is no concept of pairing. No pairing. Okay, now if pairing doesn't happen, how should I fill in the electrons? So let me sketch 3D orbital for you. Okay, so 1, 2, 3, 4, 5, and here it's 4s, and here of course, because though it's not there, so I'm going to write here 4p0 again, because that set what I discussed before, n-1 d, ns and np set orbitals are participating in the hybridization. So that's my 4p orbital. Okay, now since it's a weak field, so no pairing. Okay, so if no pairing, that means you can easily apply Hund's rule. So according to Hund's rule, how should I fill in the electrons? 1, 2, 3, 4, 5, and here is the 6th one. Understood? Now very carefully observe this. Can this d orbital participate in bonding? No, because I told you only those orbitals will hybridize which are empty. They should not have any electron, but here I can find one unpaired electron in each of these 3d orbitals, degenerate orbitals. So that means 3d is not capable enough of getting into the process of hybridization. So which is the next set of orbitals I told you previously participating in hybridization would be ns, NP and ND. So ND means I want that 4d orbital should also participate in bonding. So here I'm going to use this space for showing the hybridization. Okay, so let me just make this space for you. Let me erase all this. Okay, fine. So here we go. Now this is of course 4p, which is 3 degenerate orbitals, and here I'm going to sketch d. Fine, this is 4d orbital. So now I have a set of ns, np and nd orbitals participating in the process of hybridization. Yes, again, how many orbitals should participate? Again, depends upon the coordination number. So it's 6. Obviously, these 6 will hybridize together, and once they hybridize, you are going to get, this is the process of hybridization, and you form 6 hybrid orbitals. So here I'm going to draw 1, 2, 3, 4, 5, 6 orbitals, and the hybridization would be, now listen carefully, S, I will begin with S because S is the first orbital which is participating. P3 and D, will all D participate in this bonding hybridization? No. So here I should be very careful, since I need total 6. So I cannot utilize all 4D for the process of hybridization. So I got 1, 2, 3, 4, 5 and 6, right? So understand it very carefully. I have to use only 2d orbitals, degenerate orbitals. Okay, so here I'm going to close the box. So these 2 degenerate orbitals of d are going to participate in the process of hybridization, and other 3 are left behind. I don't need them. That's the very important point I mentioned previously in VBT, when I was discussing VBT, that the orbitals which participate in hybridization depending upon the coordination number. So I don't want all these 5 4d orbitals to participate in hybridization, because the total number should be 6. So therefore sp3, and only I'm going to write here t2. So well enough, and here again I have fluorido as ligands, and as I said, ligands possess lone pair of electrons, so they are going to donate 2 electrons in each of these hybrid orbitals. So therefore the bonding is done. So this is how ligands bond with the central metal ion, okay, and this is the process of hybridization we have to discuss. Now what are the factors we have to find out if we figure out the hybridization? So first of all, now you can see easily in the previous example it was n-1d which participated, that is 3d orbital participated, but in this example it's not the 3d orbital which is participating, it's 4d orbital which is participating. Hence the first orbital is S, then P, and D is the outer. Fine. So it is the outer orbital. Okay, I write here outer orbital complex. Very important point to be noted down. Okay, another important factor is the magnetic behavior. So you have to see the this 3D, not 4D, okay? 4D is only for the participation in the hybridization, but to decide the magnetic behavior, we have to only speak about the orbital, d orbital of the central metal ion in which the electrons were present in the ground state. So you can see here the electrons are unpaired. So if the electrons are unpaired, we come to know that the nature is magnetic. I'm going to write down here. So it's paramagnetic in nature. So it's an outer complex, it's paramagnetic in nature. Hybridization we already found, that's sp3d2. And what else we can figure out? Yes, since it's an outer orbital complex, what about its spin? Its spin is considered as high spin, okay? Because why we call it as high spin? Because here pairing did not happen. So since pairing did not happen, the spin is said to be high spin. And of course, the shape is octahedral. That is the table which I have already discussed with you in the previous video. So I think with these two examples, the things are very, very clear to you. Now, practice well for these hybridizations, and you have a lot of questions in your NCERT book. Try those, and in next class, we are going to discuss about few more examples. By then, I would like to emphasize more on learning of the spectrochemical series, that is the series which I gave you for weak and strong field. Otherwise you can't solve such questions. So that's all for the day. Okay, thank you all.